Ever pondered over the greatest unsolved mystery in the world of mathematics? What could it be about the Riemann hypothesis that has left mathematicians scratching their heads for over a century? Imagine a puzzle that has remained unsolved for more than 150 years. A puzzle so complex and profound that it has consumed the minds of some of the greatest mathematicians of the past 2 centuries. This enigma is none other than the Riemann hypothesis, a conjecture that dances on the edges of the complex plane and the prime numbers. This hypothesis, named after the German mathematician Bernhard Riemann, has become a cornerstone of number theory. It's a profound mystery, a testament to the depth and beauty of mathematics, and a tantalizing challenge for those who dare to solve it. The Riemann hypothesis is not just a problem, it's a siren song to mathematicians worldwide, calling them to unlock its secrets. So, buckle up as we delve into the captivating world of the Riemann hypothesis. At its core, the Riemann hypothesis is all about prime numbers, those solitary numbers that can only be divided by 1 and themselves. These unique numbers are the building blocks of mathematics. Think of them as the atoms of the number world. Every positive integer can be broken down into a product of prime numbers. For example, the number 12 is a product of the primes 2 and 3. But what does this have to do with the Riemann hypothesis? Well, enter the Riemann zeta function. This mathematical creature introduced by Bernhard Riemann in the mid-19th century has a deep connection with prime numbers. The Riemann zeta function takes a complex number as input and spits out another complex number as output. It's a bit like a mathematical blender, mixing up numbers in complex and beautiful ways. Now here's where things get really interesting. The Riemann zeta function has certain points, called zeros, where its value is 0. Some of these zeros are easy to find, they're called the trivial zeros, and they're all negative even integers. But there's another set of zeros, the non-trivial zeros, that are far more elusive. And it's these non-trivial zeros that the Riemann hypothesis is all about. The Riemann hypothesis makes a bold claim about these non-trivial zeros. It says that they all lie on a specific line in the complex plane. This line, known as the critical line, has the real part 1/2. It's a bit like saying that all the non-trivial zeros have been lined up neatly on a number line. But here's the kicker. We don't know if the Riemann hypothesis is true. Despite a century and a half of effort, no one has been able to prove or disprove it. It's one of the greatest unsolved problems in mathematics, and it has a $1 million prize attached to it. So why do mathematicians care so much about this hypothesis? It's because the distribution of prime numbers seems to be intimately connected to the non-trivial zeros of the Riemann zeta function. If the Riemann hypothesis is true, it would tell us a lot about how prime numbers are spread out along the number line. It would be a major breakthrough in our understanding of the prime numbers. In essence, the Riemann hypothesis is a daring guess about the nature of prime numbers, a guess that is yet to be proven or disproven. Why, you might ask, should we care about the Riemann hypothesis? What makes it so important? Well, let's dive into the world of numbers and their secrets. The Riemann hypothesis, proposed by Bernhard Riemann in 1859, has profound implications for number theory, the study of the properties of numbers. If proven, it would answer one of the most fundamental questions in this field, the distribution of prime numbers. Prime numbers, those indivisible entities, are the building blocks of mathematics, and understanding their pattern could unlock new knowledge and applications. But the influence of the Riemann hypothesis extends beyond the realm of pure mathematics. It also has surprising applications in physics. Quantum mechanics, the theory that describes the smallest particles in the universe, has a deep and mysterious connection with the Riemann hypothesis. Some physicists even speculate that the distribution of prime numbers might reflect the energy levels of quantum systems, a correlation that could transform our comprehension of the quantum world. What's more, the Riemann hypothesis impacts the digital world we live in. Cryptography, the art of writing and solving codes, relies heavily on prime numbers. Internet security, online banking, digital signatures, all these rely on the difficulty of factoring large numbers into primes. If the Riemann hypothesis were proven, it could lead to more effective cryptographic systems, making our digital world more secure. So the Riemann hypothesis is not merely a mathematical curiosity. It's a key that could unlock new insights in number theory, physics, and cryptography. It's a bridge between different disciplines, showing us once again that the universe is a beautifully interconnected web of patterns and principles. In a nutshell, if the Riemann hypothesis holds true, it could revolutionize our understanding of mathematics and the natural world. So, if the Riemann hypothesis is so important, why hasn't anyone solved it yet? Well, it's not for lack of trying. The Riemann hypothesis is a complex beast, a mathematical conundrum that has baffled and beguiled the greatest minds in mathematics for over a century and a half. The challenge lies in its sheer complexity. To understand the Riemann hypothesis, one must delve into the intricate world of complex numbers, where numbers can be both real and imaginary. It's like stepping into a mathematical wonderland where the usual rules don't apply. This is the realm where the Riemann hypothesis resides, a landscape of numbers that is as beautiful as it is bewildering. The Riemann hypothesis is a statement about the locations of the so-called zeros of the Riemann zeta function, a function that itself is a deep and abiding mystery. Despite the tireless efforts of mathematicians, a proof of the hypothesis remains elusive. There have been many attempts, some promising, others less so, but each has ultimately ended in disappointment. Yet the allure of the Riemann hypothesis is irresistible, not just because of its intellectual challenge, but because there's a tangible reward too. Proving the Riemann hypothesis is one of the 7 Millennium Prize problems established by the Clay Mathematics Institute. The prize? A cool $1 million. But despite this lucrative incentive, the Riemann hypothesis remains unproven. Perhaps it's the very challenge of the Riemann hypothesis that makes it so appealing. After all, who doesn't love a good mystery? And in the world of mathematics, they don't come much bigger than this. So, the quest continues. The search for a proof that will finally lay this mathematical enigma to rest. The Riemann hypothesis remains one of the most tantalizing challenges in the world of mathematics. So there you have it, the Riemann hypothesis in a nutshell. We've traversed the enigmatic landscape of this hypothesis, which despite its simplicity in statement, holds profound implications for the world of mathematics. It all starts with the Riemann zeta function, a mathematical function that Riemann, a German mathematician, proposed in the mid-19th century. This function, when equal to 0, reveals the so-called non-trivial zeros, the locations of which have been the subject of this intriguing hypothesis. The Riemann hypothesis postulates that these non-trivial zeros occur only at certain specific points in the complex plane. This assertion, though seemingly simple, is intertwined with the distribution of prime numbers, those unique numbers that have intrigued mathematicians since antiquity. The implications of this hypothesis are vast. If proven true, it would provide a profound understanding of the pattern and distribution of prime numbers, a knowledge that carries implications far beyond pure mathematics. From cryptography and computer science to physics and engineering, the ripples of a confirmed Riemann hypothesis would be felt across numerous fields. However, the challenge of proving the Riemann hypothesis has been as enduring as the hypothesis itself. Despite the best efforts of mathematicians over the last century and a half, a conclusive proof or disproof remains elusive. This enduring challenge has made the Riemann hypothesis one of the 7 Millennium Prize problems, a set of unsolved problems in mathematics that carry a prize of $1 million for their resolution. Whether the Riemann hypothesis will ever be solved remains a mystery, but one thing is for sure: its allure will continue to captivate mathematicians for generations to come.